because I offered to sort of cover the basics of higher order functions today, I'm going to need to proceed quickly with this material. And we are going to iterate over it in various forms over the next few days with different components of this introduction to Scala. For the next week or so, I will be walking you through, this week and next week, possibly a little bit beyond that, I'll be walking you through this Scala language with a particular emphasis on elements of Scala that are useful for functional programming and, by extension, for scalable programming for large-scale data science. Okay? We talked about some introductions to Scala last time. I didn't mention it was a multi-method language. It supports functional programming, yes, but also object-oriented programming, and you will see it in its syntax. We talk a lot about instances of classes in it, as well as about functions and applying, elements of functional programming, such as higher order functions. It does lie atop the Java virtual machine, so it's completely interoperable with Java and with tools such as AspectJ and other Java-based tools that you can use both for traditional Java and for Scala code, profilers, debuggers, etc. And has widespread use of type inference, which keeps the amount of mechanism simpler and therefore sparser syntax. It's a dominant language of data science. It competes with Python for being the preferred platform of choice. And I think it's head and shoulders above Python in a number of aspects. And it does provide excellent support for parallel programming. And also, as we'll see, a declarative syntax, a syntax that focuses on what you're trying to accomplish and less on the how. Okay? And critically, it supports laziness in a way that we're going to be talking about probably next time. And we're going to be using this interactive read-eval print loop. Okay? Okay, ladies and gentlemen, there's lots of elements of Scala. What I'm going to go into today is a particular set of discussions within Scala that we're going to be covering, which have to do with Scala methods and functions, okay? How do we define methods in Scala? How do we define the functions that make use of them? And then how do we use those functions in closures and then successively with collections in terms of this map, reduce, filter, okay? I'm going to need to go fairly quickly. I apologize for that, but I'm going to try to give you a whirlwind introduction to this, okay? So a couple of things. Scala does distinguish between functions and methods, okay? And the fundamental way that we define a method in Scala is as follows. Okay. Great. So we could say def, for example, foo. Okay, and we could take in a value n that's an integer, and we say that it's equal to, and this could be a long series of code. It could be a long series of what we'd call in Scala statements, in Java statements, but really everything in Scala is an expression in the sense that it computes a value. Okay? So if we have a very simple thing, we could just say something like this. Okay? So this is a method that does what? Great. Indeed. So it squares values, right? Okay, that's terrific. But we could write something much more complicated if we wanted to in curly brackets with several steps. And by defining a method, we can often take advantage of a variety of other features of Scala we'll be seeing later. This includes type parameterizations. So we could have foo operate on different types. It includes declaring optional parameters, named parameters that have certain default values if you don't specify them. You can specify implicit parameters, where it looks around for a value that could serve in lieu of this parameter set, and if it finds it, you don't have to provide it. it will use it from the context, okay? There's lots of things you can do, it turns out, with methods that you're not going to be able to do with functions by themselves. But ladies and gentlemen, our query today is to focus on functions and passing functions onto higher order arguments. And it turns out that you can turn a reference to a method into a function by following it by an underscore, okay? So we can say, val function foo, okay, equals foo. If we try to just say this, it's going to be quite unhappy. It's going to say, I can't find it. Actually, it's going to say, I need an argument for foo. If we want to create what's called a reference to a partially applied function, we haven't supplied the arguments. Notice it's looking for the argument it's saying, you need to provide me an integer. And it's thinking, I want the value back from foo. If I want to refer to foo as a function, I can do so here. Now, function foo is going to perform the same function as the method. It's going to be treating it in a way I can pass it around as a value, etc. Okay?
Function foo passes the concept of the squaring of something.
That's correct, yes. And it is referring to the method foo, but the method foo by itself can't be passed around. Notice when I said equals foo, it said, well, tell me what value you want me to be applied for. In order to refer to it as a function, I needed to put this underscore after it. That's a bit of an ugliness of Scala, but it's something there. And it turns out functions and methods are different. Okay, you could do things with methods, make them type parameterized, have them take optional arguments, etc. You can't do with pure functions. Okay, now, yes.
If you could define the format of that function foo at the beginning, for example, we determine that foo is an integer or a double.
Yeah.
And did we again need this underline thing?
Yes, we still would need that. Okay. And there's some technical reasons for that. I will tell you something else though. Scala also distinguishes when it comes to methods. We're going to be spending most of our time today on functions. But when it comes to methods, Scala distinguishes between a method and a procedure, or it might be called a subroutine. A procedure just performs some action. It doesn't return a value. This is actually returning a value, so we have equals there. If it doesn't return a value, if you just wanted to do something, perform update or something like that, we don't want it to return a value. It could take an argument, but then we'll just put, print updated, something like that, okay? And this will be a little method it's a method. It's a procedure that says it performs an update. Now you'll notice that Scala is also fairly accommodating with semicolons. Basically, you need semicolons when you separate multiple statements on the same line. Okay, but it's fairly accommodating in terms of leaving those out. Okay. Okay. So that's a little bit with methods, but I want to get on to talk about functions. So here we have a class where we have a reference to something. We can create an instance of that class, and we can refer to its function increment for that reference with an underbar after that, or we can just refer to the floor function rather than to the method itself using something like this. We just saw that. But ladies and gentlemen, this should actually say method formal parameters. Okay, these are things, and we'll come back to that. I don't have time to go into it, but a lot of the time we're going to be writing anonymous functions, ladies and gentlemen. We're going to be writing functions out as values that don't have nice names. Let's write our first anonymous function here, shall we?
Sure.
Okay, watch this. Function, I'm going to say val function bar, okay? We're going to have a thing. We're just going to we're going to call it bar. This is going to be a function. It's going to be a true blue function. It's going to take in an integer, okay? And it is going to return n cubed. Okay, there we go. Okay, there we go. That's actually a function. You could see it's a function here. That's the same signature that it uses there. And what it's saying is basically this is a function. It takes in an integer and it returns an integer. How does it know what it returns? Well, it's through a thing called type inference. It figures out, look, if n is an integer, this is an integer. Okay? And you'll notice that's the same type, int to int, that occurred earlier when we went from this method here to a function. There it is, right there. That's the same thing. So we converted to a function there, and this is a function from the get-go. So we could say function bar is applied to 3, and it gives us 27. And we could apply it to 0 or 1, and it gives us 1. We could apply it to 5, and it gives us 125. Okay? So this is a little function. Okay? We declared this as a function, and sometimes we don't even give it a name. Here at least we're giving it a bit of a name, but often we will create a function and pass it to something without even giving it a name. It's kind of like the horse with no name, but without without it being equestrine, equine in character. Okay.
It's the horse with no name with no horse.
That's right. Yeah, without a horse. Yeah, with a function instead of the horse. Okay. So, ladies and gentlemen, thinking about things, defining things anonymously, we could perform something like this. What do you think this is going to do?
Turns out all the cubes.
All the cube. Well, no. All the multiplies by 3. What do you think this returns? Well, there's no need to speculate about it, ladies and gentlemen. Let us compute. Okay, 0 to 10. What does that return? It returns a range in Scala. And if we say map n to n times 3, what do you think we'll get?
You triple each number.
Yeah, 0, 3, 6, okay? Notice that it doesn't require me here. Notice up here I did this, right? And if I had gone up and I had said, I'm just going to say n goes to, guess what will happen? I'll say missing type, doesn't know what type it is. It's got to start somewhere. But here, why is it that it's not concerned about that? Well,
type of 0 to 10.
It knows what type it is because this is a range of ints. It knows, okay, that's an int. This has got to be an int. Okay, so this is an anonymous function. It has no name. We didn't give it a name, right? No, it has a meaning to it. It has some job it's accomplishing for sure, but we just didn't give it a nice little name, right? Here we tripled all these things in there. Alternatively, we might square them all, right? Boom. Okay, there we go. Okay, so this is a collection, and it's applying this. It's applying this function to each element. That's what map tells it to do. Okay. We'll come to reduce. We'll see how we could do reduce right, for example, to successfully reduce things. But sure, we can put this in right now. Why don't we go put that in there? Okay, here we go. Copy, and let's go put it in. Okay. So here it's successively adding up the numbers in this range. Okay, and as Gauss observed when he was in second grade or whatever, it totals up to something with a 5 in it. He totaled up the number. His teacher Gauss, the famous mathematician, she I guess was kind of getting sick of the rambunctious kids or whatever in her class, and she didn't have material to give them, so she gave them assignment. She said, "Okay, I'd like you to add up all the numbers from 1 to 100." Yep. And she figured, okay, that will keep them going for an hour. And I think within like 30 seconds, Gauss had the answer. And it was correct. Because he realized that you could, if you're adding up 0 to 100, basically you can add 1 to 99, you can add 2 to 98, you can add 3 to 97, and they're all going to add up to 100. You know,
that's how you get the formula for some of the first integers is increment plus 1 over 2.
Yeah, exactly. Anyway, we don't need Gauss to get our answer that quickly, but could give us a lot of other better answers. Okay. Now, it turns out that Scala puts a premium on every keystroke. They really tried to make the language something where you have to minimize the number of keystrokes. And another way to write these things would be as follow. Okay, instead of writing this, we can simply write this. Okay, what that means is, okay, there's an argument to this function. There's a
Can you drag the
parameter.
parameter?
Oh, you can't see it?
A
Oh.
little bit.
Okay, it's censored in a most unseemly fashion. Yeah, just you needed the key thing. That's an underbar.
Yeah.
Okay, this is basically saying, okay, look, there's some argument. Multiply the argument by 3. Okay, it's simultaneously saying, okay, there is an argument. There's a first parameter here, and use it here to multiply by 3. Okay. So this is tripling all the numbers there, and we don't have to write this whole n goes to n times 3. We could just say whatever is given as an argument times 3. Okay? And it knows there's one argument. So this is the same function as this guy. This function can be written more succinctly like this. Okay? Notice we didn't even have to mention the int up here, that it's an int it takes in. But here we don't even have to mention its name. It's an anonymous parameter name. Now we could also do this reduced right thing in the same way. And you got to be careful about how you use these, but instead of writing that, we could just write reduced right is this guy plus that guy. And now there's 2 different arguments. Notice it's not the same one used twice. There's actually 2 different ones. Okay? And each of those stands for some argument to this.
What are the arguments to reduce right? I'm assuming.
One is the accumulator and one is the current value.
Okay.
So it's successively sort of adding them up from the right-hand side, and it's got a running total, and then you've got, well, in this case it's a running total of adding them up, accumulative total, and then you've got the new one to be added in. And it says how do you add the existing running total, or how do you combine the existing running total with the new value to yield
So if I want
the
to
result?
do parameterization, I said what is that with a multiplication?
No, this would be, it's a summation, but it's a summation from the right-hand side outwards of the expression. We're going to get to reduce later, okay? I'm just trying to provide some basics of functions, okay? So we saw how we could treat things as functions here, okay? Okay, now, notice that when I define something in this way, if I say, notice that I was able to lend this name. This is a function. I gave it a nice little name. We'll come to what this val is, but basically it's saying, hey, I've got a value, and this value happens to be a function. I'm going to give it a nice name, function bar, right? At least I think it's nice. And we could pass it to 109, and it will give us back the answer, right? Okay. So this function is something which can't be given a name, but it's the same. I would use that val also. I'd say val, val zap equals, I'd use it to refer to a number or whatever. Here's zap, right? It's just a 3. This is just any other value. Here's a value, and I give it a nice name. Here's a value, I give it a nice name. Val, baz equals, that. Val. Vap. Okay. There we are. Okay, this is just a nice name for this little value here. And so functions are just like any other values. You give them nice names, okay? Okay, so those are functions, ladies and gentlemen. Let us now continue on. So so one of the most powerful things we could do is use these little functions. Now, a more advanced topic here that I'm going to skim over, but I'll come back to, is this issue of a closure. Okay, you can have a function that returns a function, but the function it returns often needs to remember some information. Okay. So we could take, for example, a sum. You think of the sum operators as a function, right? It takes in 2 arguments and a plus b, and it adds them up, right?
Yep, that's not what that does.
But what this can do here is we can instead divide it up so it takes first one argument and returns a function whose job in life is to add whatever was given before by a new thing given to it. So this increment by function generator, it takes in a value c, which is an integer, and it returns a function whose job in life is to add c to things. You give it a value, and it will add c to it. So let's see how that might be used. So I call it here fn increment by, okay? So this is a function. It takes a function and returns a function. What's that function that it returns? It's a function that adds that value c to whatever it gets, okay? So it will get a thing called n, and it will add c to it, okay? So this is a useful function. So we could create something whose job in life is to add 1 to things by calling fn increment by 1, okay? And that will create a function whose job in life, it's specialized to add 1 to things. Or we could create a function whose job in life is to increment by 10. Okay, here's a function whose job in life is to increment by 10. Do you see that? This fn increment by. So let's trace through what's going on here. Fn increment by 1. What's going to happen? We apply this, right? We perform this. What happens? Well, c becomes 1, right? And what is returned? So fn increment by, this is a function. It takes in a c, that's 1. And what does it give back? Speak on, youths. What does it give back? Yeah, it gives back a function that takes in a value n and returns n plus 1. So this fn increment by, I give it a 1, and I get back a what? A function. And what is that function's job in life?
Take in a number and spit back out that number plus 1.
Plus 1, yeah. Its job in life is to add 1 to it. So this whole thing here is returning a value. What's that value? It's a function. And its job in life is to add 1 to things, right? And then I've given a nice name to it. Alternatively, if I call this, what does it return?
A function that adds 10 things.
Okay, so this returns a function, and what is the job of the function it returns? To take in a value and to do what? And to return
That value
10
is-
plus it,
Yeah.
right? So fn at 10. So enough of looking at slides. Let's do that. What do you think? Good or not? Okay, let's try this. Okay, so val fn increment by function increment by, right? It's a nice name for a value. What is a value? Well, it's a value, and it takes in a c. Okay, so it takes in a c. This is a function. It takes in a c, and what does it return? Well, it returns a what? Returns a function, right? And what does this function do that it returns? Takes in a function, or takes in a value, and it does what to it? Yeah, n plus c, or c plus n, either one, because it's commutative. Okay? Boom. Okay. So fn increment by, and we could fn increment by 1, and it's going to give us back a function. Okay, we're going to say, my simple increment. Okay, simple increment. There we go. Boom. Now, if I give my simple increment, so I've named it for this increment by 1. If I give it the value 1, what is it going to give me back? 2. If I give it the value 10, what is it going to give me back? 11. Okay, now my increment by 10. My increment by 10. And I'm going to give it the value 10 here. What is the job in life of my increment by 10 going to be? Whatever I give it, it'll do what with it? By the way, in this little thing, you can use tab to autocomplete.
Oh, that's nice.
Yeah. Tab. My increment by 10. What if I give this 10? What does it give back? 20. Ladies and gentlemen, this function that it gives back is a function that that needs to remember something. What does it need to remember? This function that it gets back needs to remember something. It's given n, but what does it need to remember?
C.
It needs to remember what c is. And you notice that we have this my simple increment, right? My simple increment applied to 10. It's still working just fine. Its job in life is to add 1 to things. My increment by 10 job in life is to add 10 to things. And they all were produced, ladies and gentlemen. They all were produced by this same function, right? Just apply different. So it's not just that it returns a function, it returns a closure, a function that needs to remember information. In this case, the value of c, okay?
And also the operation, this operation.
Yeah, that's true. And it's this operation in light of a bit of additional value on the parameter values, okay? So it's remembering that. So we say that this function takes a value c, it returns a closure, in the sense it returns back a specific value. Now, you can imagine a function that doesn't take anything, and all it does is print something out when it's invoked. And those can be actually really useful. So you can put them as method handlers, like when an event occurs, you undertake that function by calling it without arguments. So here's a function that takes nothing as an argument. It waits to get nothing, and then it prints something out, okay? And then we can use it as an event handler. I'm not going to go into this because I want to get to a key thing here. I want to start talking about these operations, okay? So let's start talking about these operations. So the basic deal here for the three major ones, these, ladies and gentlemen, it is not an exaggeration to say that the company of Google was built to top 2 of these. In fact, all 3, but what's most famous for is the algorithm that performs MapReduce as the basis for its search engine. And in fact, a large set of the infrastructure out there to support data science is about supporting maps and reduces, and to some degree filters efficiently as well. Okay? So these are not small things. These are actually really big in their implication. We'll see about why. Among other things, they can often be performed with elements in parallel in ways that can be highly efficient. For example, when you're performing a map over a large sequence, you can have multiple processors performing different sub-areas of that map, or GPUs, graphical processing units that perform different areas. What are these things? And reduce can be done actually in parallel, though not purely so, but it can be done in log n time, as Scott may learn in the context of his 360 course. What do these perform? Well, map performs a mapping. It's a transformation of each element of the collection. Okay. Filter basically takes a. When I say collection, I actually mean a container. It turns out we'll come back to this. There'll be a thing of beauty called monads, and you will see it with options, and you'll see it with either and try. It's actually a container, okay? So collection is one sort of container. Map performs a mapping of each element of a container. Filter takes the elements of the container and basically it basically extracts and continues on just with those that map some predicates, some true or false, some conditions, some criteria. So you might say filter all, take this array and extract all things that are greater than 0. Or take this array and extract all things whose square is above, 152 or whatever. Reduce represents an accumulation. It sort of provides a way of taking that container and adding the things up in it, particularly with collections where you'll be sort of adding up the things in there. Maybe you want to multiply them all. Maybe you want to add them all together. Maybe you want to concatenate them all, one after the other in a string. Maybe you want to separate, concatenate, separating them in a certain way. These are all examples of things that you could perform with reduce. Okay. Okay. So let's talk about some of these things. We're going to create a little array called test array. Okay, and it's going to go using the syntax we've already learned from -1 to 10. Okay. Are we ready to do that? Ready or not? Here we come. Okay. Test array. There we go. Okay. Okay. Here's a test array, and it goes from -1 to 10. By the way, can I show you something? Okay. Okay. Thanks. So you can also do until here. Okay, and this will give you everything up to but not including 10. Turns out Python is a similar thing. Until doesn't do the last one. It's like the last item in it, 10 is like a limit. It doesn't go to it. Okay, it doesn't ever reach it.
Can I put I mean, this may sound really dumb, but can I put a variable in there?
Yes.
Like
Oh,
the
you.
size of an array?
Oh, you bet you can.
Okay.
You bet. Yeah. You could have a function call there. Okay. Okay. So, ladies and gentlemen, here's our test array. Right? We already did it. Yeah. All right. We're not doing until. We're doing 1 to 10. Yeah. Okay. We're going to engage in frobbing of this. Okay. So the first thing we're going to talk about, and to avoid confusing you, I'm gonna clean that up there. We're going to be doing mapping. So what does this function do? Takes the square of each element of that array, right? Why don't you do it? All right. Here we go. Test array, autocomplete. Tab is your friend, right? No option space in this. No worry about Mac issues. Yeah. How could I write that? You might say, how could I write that more succinctly with underbars?
I tried.
You can't.
Work, yeah.
You can't. Why? What will happen?
Because there's more than one underbar.
Yeah, if there's more than one, so you'll be thinking, oh, it takes 2 arguments, just like reduced did before. It takes 2 arguments, and then you'll be an unhappy camper. Watch this.
But I could write a function that returns a square and just call it on it.
If absolutely you can, you bet. See, it's basically it's looking for 2 things, and this is its awkward way of saying it. Okay, so n to n times n. Boom. Okay, there we are. See that? Isn't that a thing of beauty? Beauty or not?
Very nice.
Yeah. Okay. Okay. So suppose we.
Basically,
Yeah.
you can use the map function to create to do math on your
Yes.
stuff.
Yes.
In any way you want.
Well, it's element-wise, right? It's
Well,
applying it to each element in
So I
isolation.
can't do matrix multiplication without more work. But
Without more work, yeah, exactly. Okay, ladies and gentlemen, how if I wanted to add 1 to each element? What would I do?
Underbar plus 1.
Okay, I could do underbar plus 1. I'm just going to do it this way at first, and then with Krugerian inspiration, we could do this, right? Here we go.
Okay.
Right? That will give the same answer. This is the same function as that. We just.
Could we also call function increment by 1?
Mm-hmm. Yeah, let's do that.
Sorry.
Function. What did we call it? You folks are probably. It was called fn increment by 1, for example. Let's put it this way. We could either do this, Scott. We named it my simple increment, right? So if you folks followed me in that, you could paste that in, my simple increment. And then, or you could do, fn increment by, what did we call it? I call that fn increment by, okay? Okay, no, for some reason it's not doing autocomplete, so increment by 1, okay? Or I could add, how would I add 100 to it?
100.
Sweet or not? Sweet. Okay. What's that?
But now, how could I do that? Now, how could I do that? Could I just do like test array dot toString dot my simple increments and get the same result?
Meaning, yes, but it wouldn't be, what this is giving back, you'll notice, is not a stream right now. It's giving back an index sequence. So if you said toStream here, it would actually give back something, but this stream, you notice that this stream is lazy. It's not evaluated. It's only going to do the first one, and it's going to be waiting for you to say you need more before it actually computes it. that's why these things are all performed incrementally, as we'll see. Because it actually waits until it's needed, and then it does all the queued up work.
Oh, okay, so it's basically just-in-time programming.
Yes, and it does all the work needed to make it happen, all the steps successively. Boom, boom, boom,
But it starts
just
at
like
the-
that.
But it starts at the end when it knows it needs it.
Yes, when it needs to consume it,
So if you put a
which allows for,
That's literally a Kanban system for programming.
yes,
Wow.
yes.
If you do a dot sum at the end, then it'll give you a sum.
That's right, but it'll actually be performing them incrementally. It'll be doing the first one and having the contribution to the sum from that, then and it can throw away all the stuff needed for that, all the intermediate results, and then it will do the next one, add that into the sum, throw away all those things it computed, do the next one all along the way. But, ladies and gentlemen, I am set to finish by 12 o'clock, and before the clock strikes 12, I am determined to try to expose you to additional beauty, okay? No, I share your excitement. What does this one do?
Which one? Bottom one?
Its absolute value is all the value.
Not quite absolute, because it's greater than 1. Everything that's greater than 1 is just used the same, but everything that's less than 1 is minus of it, right?
Well,
Which it essentially becomes the same. Yes, you're right. Yeah.
Oh my
Yeah.
God.
So you could do that. Of course, there's a much nicer way to do it, but the point is you can have a conditional transformation, okay? And this is how you'd write no question mark and colon operators in Scala. No ternary operator in that way. You write if else. Notice if else is an expression in Scala, not a statement. Okay, so this
Can
is
you use then instead of brackets? Do you have an if then else?
sorry, instead of brackets. No, you mean like a function, something like that. You're saying?
No, nothing. I thought I saw an if else statement in Scala that had a then in it, but
It seems to want a response when I type it in.
you have to end another, probably in brackets.
Okay.
There you go. Thank you.
Okay.
I had the
Okay.
same error.
Okay.
Okay. So, ladies and gentlemen, so mapping will well, we've just seen it, right, interactively, right? Okay. Here we go. There's some weird delay issues. Okay. You can pass along closures, right? You can do this. You could pass it to that, etc. These are functions. We can pass any function. This return to function. Remember that? Fn increment by return to function, whose job in life was to add 3 to things. So we could just pass that function to map without giving it a name, right? Right? Yeah. So remember, Fn increment by, its job in life is it returns a function, right? There it is. Boom. Boom. There it is. There's a function it returns.
And that's
Its job in its
and
function's
that
job in
function
life is
a
to.
predicate for our statements or the argument.
Yeah, that's right.
argument.
That's right. And here we're doing it as a stream, but I didn't. It wasn't my intention. But okay. So now let's talk about reduce. Okay. Now notice that reduce has a different so-called signature. I've had these up here. So what does this signature mean? Well, if we have a container E, we apply map to it by doing dot map. We need to give it a function that maps. Now, you notice this function goes from one type to another. This is a container of E. It may be a container of ints, right? But we need to give it, when we say map, we give it a function that might return an int, but it might return something else. Might return, for example, a double, right?
He's very excited to get out of that room.
Yeah.
Or someone else was.
Yeah.
Yeah.
So this might be a container of ins, but a sequence of ins, a range of ins. But we apply it with a function that doesn't return an int, but returns a double, right? Maybe a square root operator, right? In which case, we're going to get back a container from the map. We're going to get back a container of what? Suppose we give it a function that returns a double. What are we going to get back here? Container of doubles. So let's try that, right? Okay, now as normal when I'm ad lib, I'm at risk here, but what the heck? Let's give it a try. Now Scala.math.square root. We could import. I think this is correct. We could do something like that, and there we go. Oh, okay. Look at that. Okay, but don't get rid of the stream, the two stream.
Yeah.
Sorry, I did that. Okay, here we go. What do we get back here? Yeah, this is sort of a crude representation of I. It just maps it to not a number. Why is that? It was the square root of what? -1. Here's 0. Here's 1. Notice that this was a sequence of a double. It's a container of doubles, right? But meanwhile, if I had simply given it, n goes to n plus 1, what would I have gotten back? A sequence of ints, right? Eh?
No.
So how does it know? Well, it knows square root. It knows what type this guy must be because the array is a remember test array is a thing of ints, right? It's a range of, and it knows those are of ints. So this guy has to be an int, and when you take the square root of an int, you get a double. So it generates that accordingly. Here it knows, okay, I've got ints coming in from here, and so it takes each one and adds one to it and knows it's going to get an int. So it does that. Okay. The point is can map to other things. Let's talk about reduce. What does reduce take? So this guy took some sort of function that could return the same thing as here, or could return a different type, and returns back a. Whenever this function returns, we get a container of that thing back, right? Reduce takes a function that takes two types of things. One is something that's accumulated. It's the same type that it returns. So maybe its job in life is to successively add up values, integers, in which case the function it takes returns an integer, it takes two integers in and it returns an integer. The other hand, maybe its job in life is to add up the reciprocal of numbers, in which case maybe it takes in an int, but the running total is a double, and it returns a double as a result. And then this return, so you give it a function like that, and then it returns whatever this function returns. It returns a summary value across the whole thing. So here we're applying a function to sort of summarize the entire container. Let's try that. Okay, let's give it a try. Test array dot reduce. Okay, I'm gonna do one reduce operator. It's going to add things up like that. Okay. Now maybe I should have done things in more explicit way. Maybe this takes in a value and an accumulated value, and it returns n plus a. That would have been another way to put it. I just abbreviated it by my sort of saying, okay, leave those out. But
we're to define the a here.
Well, this a is what's given to me, and the initial value is going to be from the last value of the array. Of the collection. Now it turns out that there's a fold operator.
Fold
needs the initial. Man, you're really good. This is great. Yeah, that's exactly right. So we could have fold, and fold will actually allow me to say start with an accumulator that's like some value. So I could say start with an accumulator, and then use this as the thing to add up. And you notice it gives me the same thing. But if I started with an accumulator of 100, what would it give me?
154?
154. Now, so fold is the same there. Now notice something funky is going on. What if I say this? It's going to say, hey, you can't do it. Notice something's funky. Fold actually takes two sets of arguments. First it takes this, and then it takes this, okay? So if I actually went, it's what's called a curried operator. So if I actually went like this is a partially applied operator. It's just waiting for me to give it a function, and it will perform the fold with that function.
I'm sorry, what's the fold to?
The fold, it performs something like reduce, but it does so with some additional types of options, including you could give an initial value for the accumulator. For reduce, it always uses the last value or the first value, depending which one you use, in the array, in the collection, as the starting value.
So how would I'm trying to use
Let's-
reduce to calculate the average of the data set.
Yeah, so you unfortunately have to sum it and divide by the number in it, which is deeply unfortunate. It's another thing. But watch this. Let's do reduce. Let's not get caught up so much in just this operation. Suppose I want to reduce this in a way that concatenates all of the things together as strings. Okay? I want to list them one by one as strings. Okay? How am I going to do that? I want to separate them by commas. How would I do that? Of course, for so many of these things, there's already built-in things to do it, but don't get caught up in that. The point is in the concepts. How would I do it so that it lists the elements of this test array out?
Is it like a dollar
What's
sign
coming?
in front of a, like within quotes or something?
You can do that sort of thing, and we'll be coming to that. But
Can't we simply declare the accumulator as a string?
well, this is what you could do. Yes. So watch this, and this is kind of what it is. What would I? Well, it turns out plus is the concatenate operator, so I could do something like this. Right? Required int. Oh, okay. Mumble. Okay. Nice thought. Killed by an ugly fact. Okay. So it found. So why isn't it liking that? Okay. Pardon me while I muse. Okay. So let's do N and C and. Okay, so what's going on here? It's a type mismatch. It found a string, and it was expecting an integer. Okay, yeah. So what is the matter with this? Gosh, I would have expected this, but I know what it is. I think. Okay, let's try this. Let's try the fold. Do fold. You could see there's a couple folds. And I'm going to start it with this, okay. Okay, now this can be a problem with this, but we'll learn from it. And now I'm going to do this thing here. Okay, we're going to start with a string, and we're going to successively concatenate it. What's the problem?
Initial comma?
The initial comma, right? This is the value it's starting with, and then it's going to put a comma after that, which is not quite what we want, right?
Can't we simply trim it?
Yeah, we sure we could very easily trim it. Let's try fold right, see what that does. Well, that actually starts from the right-hand side, eh? That actually starts from the far right side, and you'll notice the point is it starts with this, and then it successively adds this in, okay? And the problem was up here it was starting with the first element of the array and then trying to add it in here. Okay, and it actually, okay. So here, ladies and gentlemen, it's not quite what we'd like, but you see that basically you can tie together the elements of the array with that. Let's suppose we wanted to multiply all the elements of this array. How do we do that? Instead of adding them up, suppose we want to multiply them. Good. Yeah. 0. Why is that?
Zero among it.
Okay, yeah, so 0 among. How if we want to multiply
Without the zero if statement.
yeah, right. How if we want to eliminate the 0 first? How do we do that?
Filter.
Yeah, let's do a filter up front. Okay, and this is going to get us to our filter. So what would we write to filter it?
Equals 0.
Well, okay, so we could
No.
write, okay, we're going to filter a value based on whether the value is not equal to 0. So we could write it this way, right? Right? But what's a more succinct way we could write it? Underbar. Boom. Right?
Oh, nice.
Alternatively, just to see what you get out of this, here it's stripped out the 0, right? Good or not? Good. Okay. You could do right. We could do max of these. Okay. Concatenating the array elements. We could have done that as well with fold. Right. If we had folded, I should have showed that. But here we could do something like this. There's all the array elements and all their glory. Right? A thing of beauty. Okay, so now we can do that. We could take the maximum. Okay, this is incorrect. I need to update this. Okay, so there's fold and then there's reduce. Fold actually takes first the seed value, the value to use as the start of the accumulator, and then after that's specified, potentially at a later time, you could specify what what operation you want to perform on it. Okay, so it's what's called a curried function. It's kind of like that increment by thing earlier, where we gave it one of the elements, the C, up front, and then it waited for the later elements. This whole idea of currying, taking something that often occurs together all at once, like you have to provide all these different things together, and separating them out so you can provide them incrementally, is a recurrent theme in functional programming, and we call it currying. We take part of them and we specify them early, we stage the computation, we take others, we perform it late. So let's perform some filtering.
Is this that allows for orthogonal computation?
Yes, yeah. So yes, it does. And allows you to sort of do part of the work up front, and then do the part that needs to be specified later together without having to keep around all these parameters for later.
Basically, it's a way of allowing us to basically farm out part of a function among, let's say, a bunch of cores, and then when we get it back, then we can do the rest because we can't do it until then.
Yes, that's correct. You can do that. Yeah.
Interesting.
Yes, exactly. You could perform part of the computation where everything is known up front, and just keep the part where it has to be done later for when the data comes in, for example.
Gotcha.
Right? Okay, so think about a ray tracing situation where you could actually do a lot of the computations up front for a room of known size and everything, and then actually when there's some detail like an object in it, then you perform extra computations there. Okay, so ladies and gentlemen, let's filter out all elements that are even. Or all elements that are greater than 0. How do we do that? We only want to keep elements that are greater than 0.
Just add a dot filter underscore greater than
Good.
0.
There we go. So we're on to filter here. Suppose we want to keep those. Okay, suppose we want to keep those whose square is greater than 0. Sorry. Yeah, square is greater than 0, sure.
Same. Shift 6, 2.
Oh, does it take carrot as an exponent?
Or shift 8 underbar.
Right. Okay. Suppose we want to take those whose square root is okay. Trying to give something easy. Okay. Okay. Suppose we want to take something whose cube is greater than 0. How do we do that?
It's the same.
The same. Yeah.
I
Okay.
think we're all with you.
Yeah. Let's just do it. Okay. There we go. All right. But what's another thing we could do? We have another option for this. What could we do?
You could ask, suppose we want to filter on which elements exist within the Fibonacci sequence.
Okay. Yeah. You should see Fibonacci. It's going to be beautiful.
That would be more
In
complicated.
streams. Okay. Ladies and gentlemen. Okay. So another thing we could do here, you notice we have we could actually perform a little computation. Alternatively, we could do this, right? We could map it first to the cubes, right? And then just test if they're greater than 0. And generally, it's kind of nice to decompose it orthogonally. So here's the computation, here's the actual test, right?
But we lost the original array. And now the array is the
True.
array.
That is a good point. That is a very good point. So here we're actually reporting which of the original n's match this, whereas there we were sort of operating off of this intermediate array. Yeah, this array there. Okay, good. Okay, we're closing in on time here. Okay, so let's filter out things which are even. How do we do that?
Mod.
Underscore mod 2.
Yeah, and you can actually do it like this. And I'll put these in for ease of reading it. So this takes its modulo. So basically, what's the remainder when you divide it by 2? Okay. So 3 is modulo 1, 5 is modulo 1, 4 is modulo 0.
Could we write a function that would find the prime numbers?
Yes.
By recursively calling a modulo operator?
Yes, you could do it with modulo. Yes, absolutely. And in fact, we will do something a little bit like that in a future session. Okay. Okay, ladies and gentlemen. Suppose we wanted to test things that are between. By the way, how can we write this more succinctly?
Just
Under bar, right? We don't need this. If we look at that. Okay. Mumble. There. Okay. Yes, it is. Okay. Mumble. Okay, that's really interesting. Why it interpreted that. But in any case,
Those shouldn't change the value.
yeah, you wouldn't
it's not
think.
Lisp after all.
No. So here we go. Okay, suppose we want to look for things whose value is between 2 and 6. How do we do that? 2 and 6 inclusively.
And with greater than and less than.
Yeah, exactly. So n is so inclusive. So n is greater than or equal to 2, and n is less than or equal to 6, right? Make sure we've got our balanced parens, yeah? There we go, all right? We're filtering them out.
So.
And suppose we want to square them now.
Oh, then we have.
There is, at the beginning, there is like 2 to 6 is okay or not?
Sorry?
At the beginning, you have used the -1 to 10. It will be -1, 0, 1 to 10. So here, if it's 2 to 6,
Yeah.
okay?
If it's 2 to 6, meaning, so here's the original one.
Yeah, I think just change the n greater than 2 and n less than 6 to n to 2 to 6.
Oh, I see what you're saying. No, that 2 thing, like I2J, that's actually used to generate it. So it's actually not it's not a predicate. It's not something we can test the value.
Is there a match?
Yes, is there a match.
yeah,
You will wait to see matches.
The reason I say that is basically the idea was if I want to filter a set so that I want all the elements in this set that are contained in the other one.
Yes.
That's what I want to do, and that's I think that's sort of what you're again. Give it
Sure.
a container, and then give me all the elements that fall in it.
Yes. Yeah. Yes, there are. I think there's a function, especially to do that, a method to do that. Okay. So, ladies and gentlemen, in this whirlwind tour, we have looked at how we can use map, filter, and reduce, and we've tended to look at them, independently here, right? But suppose here we were to, as the sort of crowning glory, suppose we wanted to to total up all the numbers between 2 and 6, just like this. We wanted to take their squares and sum them up. How would we do this? Or take the product of all their squares. What would we do? So we want to take all the numbers in that array between 2 and 6, which happens to be all of them between 2 and 6, but it could be an arbitrary array. We wanted to take their squares and we wanted to multiply them all. How do we do that? Dot map. Good. And we could, how would we map to what? Into n times n, and then we'd want to
map or reduce.
We could reduce them, right? Oh, look at that. Okay, I mumble. But I just pressed tab to autocomplete it. Okay, it was an unhappy autocomplete.
Right.
Okay, and then dot reduce, and what do we put here? Yeah, there we go. Okay, that's it, ladies and gentlemen. Boom, there we go. That's our answer.
Interesting.
That's our answer. And of course, this is not specific to this test array. We could create a different test array. Here, watch this. Test array 2 equals array, minus 3, 2, 5, and 100, 1241. Val. I should have done val. There's my value, and of course I could have applied this pipeline to those, right? There we go.
So can I create a function that basically returns everything after that first dot?
Sure.
So I can just write test array, for every test array I have, apply this to every single test array.
You bet you could. Yeah.
Seems useful.
Yeah. So def. My pipeline, something like that, right?
Mm-hmm.
And it would take in, let's say, this is an array of int, right? It would take in perhaps an array, right? That's an array of int, okay? And it would then return, right? It would return this array dot filter
And all of that.
all of this stuff, right? Copy, paste, right? Boom.
Well, you need the filter on there.
Did I not?
You didn't copy the filter as well.
Oh, I didn't copy the filter. Okay, thanks.
Oh.
Filter, boom. Okay, so
That's amazing.
there's my thing, and then I could call it my pipeline on test array 2. There we go. Right. Now, could I call it on test array? That's an interesting thing because it's actually a range and it wants it. But one thing I could do is do 2 array. There we go. A thing of beauty, ladies and gentlemen. A thing of beauty and a key tool in data science. So next time we're going to build on this, and we'll be talking some about the collections on which we're performing these things, but we'll also be going on to discuss some additional aspects of the methods, and we might start laziness next time, otherwise it may be referred to next week, okay?
You're procrastinating about laziness?
Yeah, that's right. Okay, ladies and gentlemen, thank you very much for your attention. Thank you for your patience. And I will look forward to seeing you on Thursday, right? Hope this has given you some additional understanding of map, reduce, and filter, which are key building blocks of today's data infrastructure for large data. Thank you.